Well, good afternoon. It's 5:03 p.m. on the Thursday, the 25th of July, 2019. It's supposed to be Physics 112, and unfortunately, I'm the only one in the room right now, so I assume some of the students will be coming in. They always do, but right now, I'm it. And normally, I would make announcements now and find out if there were any questions and that type of thing, but with no one in the room, I'm not going to do either of those, so I'll just wait till someone comes in, and then I'll make the appropriate announcements. And because it is near the end of the term, and I want everyone to understand where I'll be, when I'll be, that type of thing, and how to wrap things up. So let's go from the current slide, which is a blank page, if it'll come up. So far it's not coming up. There we go. All right. We're in Chapter 17, which is Basic Electricity. We're in 17.4, Electric Fields, and this is the on page 457. Okay? Now, I don't know why it went to there. So far, we have discussed electrification due to the brushing of electrons from a surface, and that basically is what we call static electricity. The concept of electric field is also an important part of the study of static electricity. Two magnets may either attract or repel each other, even though they may not be touching, and we saw that in the electroscope too. Even though you don't touch something, you can create a field. So to illustrate the idea of a field, even though they're not touching, there's an invisible region around each magnet. Now, I don't know why they're talking about magnets now. You could just as soon be talking about charges, and that would be electric. Next, chapter 18 is magnetism, so you could talk about the magnets there. But in terms of static electricity, an electric field exists. Let me get my pen set up. Okay, an electric field exists where there is an electric force when we did electric force with Coulomb's law, where the electric force, and this could either be attraction or repulsion, attraction or repulsion, acts on a charge brought into the area. Okay. Now, I don't know if this helps or not, but just like we saw before, and make some illustrations of it now, if you had a charge out here somewhere, it could be a positive charge, it could be a negative charge, it doesn't matter which it is, just out here, and you brought another charge somewhere into the space fairly close but not touching that charge. If that charge you brought in was the same sign as a charge that was already there, then you're going to have trouble getting that charge to get closer because it's going to be being repelled. That's the electric force, okay? And we did Coulomb's law for it. Well, look at that. Nothing's touching that new charge that you're bringing in, and yet it's being repelled by the existing charge. Or if that new charge you bring in is the opposite sign of the charge that was already there, then you have trouble keeping it from flying into it because unlike charges attract each other. So either attraction or repulsion, you would have a hard time. You'd have to hold back that new charge you brought in to keep it from racing into the opposite charge that was already there. Well, they weren't touching, and yet you're having to exert a force to either keep them apart or push them together, but nothing's touching each other, that means there has to be an electric field in the area that's doing the pushing or the pulling. Okay? Now, there is a picture in your text, it's not in the slide set, of a balloon, and what they've done to the balloon is probably taken some wool cloth or something like that, rubbed the balloon vigorously with that, which is probably taking electrons off the balloon, making it positively charged. I'm just guessing on this now. And you put it against the wall, which is neutrally charged. Well, that's going to stick to the wall because it's trying to grab a hold to those electrons in the wall to replace those that it lost when you rubbed. So that is an example of an electric field holding that balloon onto the wall. Now, electric fields can be measured using test charges, and that's what I just sort of implied. And here is the formula that we use to describe an electric field. The electric field E is equal to the electric force that we get through Coulomb's law divided by Q prime, where Q prime is the test charge measured in Coulomb. Now, if you remember what the Coulomb's law was, that was K, Coulomb's constant, or electrostatic constant, times Q1, Q2, divided by R squared. Well, this Q prime is basically one of those two charges. You could make it Q2 and make that Q prime, and then these go out, and the electric field is then K Q1 over R squared. Okay, now if you remember what the units for K were, they were newtons, meter squared per Coulomb squared. You multiply that by 1 Coulomb, okay, by the Coulomb for this, and divide by meter squared. And the meter squareds go out. One of the Coulombs goes out, so the unit for electric field is Newton per Coulomb. So many newtons per Coulomb, which is exactly what we have here. A Newton divided by a Coulomb. Electric field is measured in newtons per Coulomb. The result is a vector quantity, just like forces are vector quantities. Charges are scalar quantities. No direction associated with those. They attract or repel, but that's not a direction. They just attract or repel. The force is a vector, and when you divide the force by the scalar, that just scales it down or up or whichever, and that produces electric field. So in reality, that's a vector quantity. That's a vector quantity. Q is not. Okay? Let's do example 1. I think I will erase the slide here, put back on what we need later, but it's want to have enough room for it to make sense. A positive test charge of 30.0 microcoulombs. Okay? Now to remind ourselves, what's micro mean? 30.0 times 10 to the minus 6. It's 1/1,000,000th of a coulomb. Okay? That's your test charge. Is placed in an electric field. The force on it is 6.600 newtons. So this, by the way, is your charge, Q prime. Okay? The force, when you place it in this electric field, the force is 0.600 newtons. Okay? What is the magnitude of the electric field at the location of the test charge? Okay? Well, the electric field, and that's a vector quantity, by the way, and this is 2, is equal to the force divided by the charge, Q prime. So this is going to be 0.600 newtons divided by 30.0 times 10 to the minus 6 coulombs. Okay, now, that's a fairly awkward looking division there. And how I'm going to make that a little bit neater and easier to calculate, I want to move this decimal one place to the left. Okay, so that made for a smaller number, so I'm going to have to increase my exponent here by 1, so that would be to the minus 5, not minus 6. Okay, now, I think about the same time, let's go on and make this a bigger number, which means now we're going to be times 10 to the minus 1 newtons. Okay? 6/10 of a newton is the same as 6 times a tenth of a newton. So that's 6/10 of a newton. All right, now let's see what we can do. 3 will go into 6 2 times. Our significant digits are 3, so it's 2.00 times 10. And when you're dividing exponents, that would be a minus 1 minus a minus 5. Well, minus a minus is plus, so minus 1 plus 5 is plus 4. Okay? And that would be newtons per coulomb. That's a pretty healthy seeming electric field. That would be 20,000 newtons per coulomb. The force is rather small. The charge was extremely small, but the field would be 20,000 newtons per coulomb. And they got 2.00 times 10 to the 4th newtons per coulomb. Okay? Good deal. Now, have you ever used any electric fields? You might say, no, I doubt if I have, but that's not quite true. They show on the top of page 459 some electric fields. If you have ever watched the television or looked at a computer screen, electric fields are used for many applications of electronics and elsewhere. An inkjet printer uses electric fields, varying electric fields, to shape the letters that you're wanting to print, direct the ink to where you want it to go, all done by electric fields. Okay? Now, another thing they suggest here is electric fields are also involved with thunderstorms, so lightning safety. Now, this is a rather bizarre looking illustration here, but it's probably not too bad, and I know what they're trying to communicate, but it just seems a little bizarre. So here's the guy out on the golf course, and he starts hearing lightning. He starts hearing thunder, seeing lightning. Now, it doesn't look like it's lightning or thundering that day. It sure doesn't look like, but he's just being a good sport about and showing us here. So he's hearing some thunder, lightning's close by. What would be your temptation? You might say, hey, well, there's a good thick grove of trees. Let's run over to that and get out of the rain. Wrong. Not a good idea, because the trees are much taller than he is, and they would attract the lightning more easily. Okay? So no, don't get under trees. He's out in the middle of a golf course, and that's pretty open. So what he wants to do is form as small a profile as he can, so he gets down in the sand trap, which usually is a lower elevation, gets down into a crouch, and then just because the thunder's so loud, he's covering his ears. So covering your ears is not that necessary unless it's very loud thunder and you don't want to damage your hearing. So that's actually not a bad illustration of what you should do if you're outside, isolated when a thunderstorm approaches, because you can become the conduit through which that lightning tries to reach the ground. He did a good thing, get down in the sand pit, crouch down, so he's not a large target, doesn't have a large profile. Don't go toward the trees, because they are a large profile. They would be more likely to get hit than he would. Neither do you want to be near the post. Okay, we finally got a student here. So, I'll just go from where I was, and that is that we just finished 17.4, and there are problems there 1 through 7, any of the odds 1 through 7. There was only one example. I did that. It's on this, well, you can't see the screen. Let me get up. This chair is gone.
If you want to record, you fine.
What's that?
If you want right here at the railroad tracks,
Yeah.
at the back, it's been a bad accident.
Oh, wow.
I've been on that road. I just sat there thinking
Uh-huh.
that I would soon get by.
Right.
I had to turn around and come around Denison
wow.
and come up. But that thing is long, and they got all the fire departments
Oh, wow.
and stuff up there.
I wonder if others are caught by the same thing.
I don't know.
Could be, because y'all are usually here early, if not just on time. Hey, there's our screen. So there was example 1 in section, the only example in section 17.4. Okay, let me
catch my breath.
what's that?
Okay, 17.
So Sharon's here. All right, I guess I'll go on and make the announcements, even though if the others come in, I'll repeat them over and over again like we've done before. This fell off.
This is 17.1 example.
This is 17.4, example 1. Okay. Now,
I don't know why I keep my glasses on. Now I can't see. Just
what's that? Oh.
Here in time.
Yeah. Okay. Yeah, that was on page 459, I believe it was. Oh, yeah. No, 458. Bottom of 458. 17.4, example 1. And we're just about to start 17.5, which is simple circuits. But before we do, the announcements, and here's what they are. I don't know if you've already done the student course evaluation, but if you haven't, please do that before the end of the term. Okay? Now, number 2. Okay? Want to go over what my schedule will be for the rest of this term. We don't have much term left, but let me explain what's going on with that. Okay? Today, we'll have class, and then when class is over, I'll be here for a little bit, but then we'll be heading on away. So Monday, let's start with Monday. Monday is the last day of class for Monday, Wednesday classes. So I'll be on the Bessemer campus from 8 to 8:30, and then we'll be leaving, Bessemer campus 8 to 8:30. Then I'll be in class from 8:30 until 5:25, just like every Monday and Wednesday. Then I have office hours again from 5:30 to 6. Okay, so that's Monday. Tuesday, not quite a normal day, but close to it. I'll be on campus from 8 to 8:30 in the office and setting up my classroom. Then I'm in class from 8:30 until 10:45. And then I'm in the office again from 10:45 until probably about 1:30. Now that's different. Why is it different? I've got an eye appointment that afternoon at 2 o'clock. It's across the road from the Bessemer campus at the UAB West Hospital. So I'll go across there, have my eye exam, and hopefully get back. Hopefully within an hour, but the last time I had an appointment on 2 o'clock on a Tuesday afternoon, it may have been a Thursday that time, I was over there for at least 2 hours. So I hope it won't be that long, but I can't guarantee it. So whenever I get through with that, I'll go back to the Bessemer campus, and then sometime before 4:15, I will leave to come over here. And we'll have our last class then from 5 until 6:30. Okay, next Tuesday. All right, let's move on to Wednesday. Wednesday, there's no more classes, so I'll be in my office from 8 in the morning. This is on the Bessemer campus. From 8 in the morning until about 1:30. Why 1:30? They've called a meeting at 2 o'clock. No, I'm sorry, 12:30, because they called the meeting for 1 o'clock. So I'll have to leave the Bessemer campus, come over to the Birmingham West campus for a meeting. It's going to start around 1, and this is one of those meetings that last a while, so I'm going to guess it's going to go at least 2 hours. Okay, but whatever time it's over with, I'll go back to Dr. Pruitt's office. That's where my office is, in B122, and I'll work there the rest of the afternoon. It's just not worth it to drive back to Bessemer and then turn around and drive home. So I'll just work on the Birmingham West campus from the time the meeting's over. I'm going to guess around 3 until 6. Okay.
So I can drop my test off Wednesday?
Say again?
Can I drop my test off Wednesday?
Yeah, if that's going to be better for you.
Yeah, then I can head back out.
Okay.
Yeah.
Is that better for you?
Yes.
Okay. So Wednesday morning or Wednesday afternoon?
Wednesday afternoon, I find it better over here.
Right, okay.
Because, the traffic be dying down.
Right. Okay. I may be there before 3, but even if I'm not, even if the meeting goes long, if Dr. Pruitt's secretary is there, Ms. Rose Saxton, you can give it to her, and then when I get back to the office, I'll get it and try to grade it. So that means you won't be here that Thursday night?
Right.
Okay.
If I can drop it off, I can.
Yeah.
If I can drop it off, I can.
Okay.
And then that way I can head back home.
Okay. All righty.
And then I have a summer for a little while before I start in August.
Right. Okay. Okay. Well, then, in that case, do you remember if any of the other students did not want pork on their pizza? I know Brianna wanted pepperoni. You're the only one? So what I may do is just get 1 pepperoni pizza. Would that be enough for the 4 of us?
Yeah,
I would think so. So I may just go to that then. Okay. That's beside the point, but since you said it, I'll bring it up. So that's Wednesday afternoon. Anytime after 1 o'clock, I'll be on the West Campus, but I may not be available until maybe close to 3 o'clock, 2:33, something like that. But I'll be there the rest of the day. Okay? And remind me tonight to give you the test before you leave. Okay. All right. But we'll have class then on Tuesday, and we'll talk about how far we got and what questions you could need to do or may avoid doing if we didn't get that far. All right, so that gets us through Wednesday. Thursday is my last day on campus, I think, for the summer term. Now, I heard the dean came out with an email that was just totally wacko, so I've got to work that out. But I'm going to be requesting to take Monday off. So I've got to have everything in by Thursday. So where I'll be on Thursday, Bessemer campus from 8 until about 4 o'clock. I'm going to leave Bessemer campus to go pick up the pizza and then come here. Hopefully we'll be here by 5. And then those that come and turn in their tests can be eating pizza while I'm grading the test. And then I can't return the test, but they can see what their scores are and what they're wound up with.
Well, shoot, I might just come on Thursday.
Well, if you want to, you can, but it'll be on Blackboard.
Just do 1 pizza, because, I've been ate before I came. I eat on the road. Please don't back me another pizza. Because that'll just be something you have to.
That's all right. That's not a problem. We'll talk about this Tuesday.
Okay.
You can decide on Tuesday whether you want to pick it up Wednesday, because you need that extra day, or whatever. So, but I will, as soon as I get the grades done, I'll put them on Blackboard, and you'll be able to see from home or wherever what your score was. Okay. Don't forget to do your student course evaluation. Okay, so if you were going to go to Bessemer campus, get it in before 4 o'clock on Thursday. If you're going to turn it in here, get it here before 6:30 on Thursday. Okay, and because I'll stay here till 6:30, but after 6:30 I'll be heading to the barn. Okay. All right, so that's how we wind up the term. I'm going to try to get grades in by that Thursday night so I can take off and go on
On your home trip.
what's that?
To your home trip.
Yeah, going over to Georgia. Or at least we're planning to. All right, so let's move on to 17.5. Okay, all right, to erase this one?
Yes.
Okay. Have you got enough light?
Yes.
Okay, all right. Okay. Simple circuits. Now, up till now, mostly what we've been talking about is static electricity. Rubbing amber with wool, rubbing glass with silk, or rubbing a comb, through your hair, whatever, rubbing a balloon with wool, whatever. That's been static electricity. Beginning in 17.5, we're going to be talking about circuits, okay? And when electrons are moving in a wire, you produce what they call a current, okay? So static electricity is just moving electrons around. Current is when you have moving electrons specifically through a wire. There are two types of current. The first is called direct current. Okay, direct current is when the electron current flows only in one direction. Okay, let me give you just a real quick example of direct current. Anything that's powered by a battery is going to be direct current. Because what a battery does is collects charges from whatever your medium is on one pole, and you have a deficit of charges on the other pole. You connect it, and the charges run from this pole to that pole. Okay? All in one direction. Okay? Now, you don't absolutely have to have a battery, but batteries are indicative that it's direct current. So if you think about it, your car is direct current. Just about everything in your car is direct current. Why? You've got a battery there in your car, right? But there is one exception to that. If all you were doing was running off your battery, you'd run your battery down. So your car is also recharging your battery all the time. But that generator that recharges your battery, that's alternating current. Well, that wouldn't charge your battery because it would charge half the time and discharge half the time, charge half the time and discharge. So your battery would never fully charge. It would stay right about where it is, actually get a little weaker. Okay? So what they do, they have a device in there. Used to be called a split ring commutator. That's a fancy word. Nowadays they use something called a dual diode connector. It's an electronic thing that for half of the cycle of that alternator, it sends the current this way. For the other half, it sends it in the same direction, not in the opposite direction. So every half spin, it sends, so you get a pulsed direct current. Okay? That's direct current. You don't need to know that, but just in case. Now, how about your telephone? Is that associated with a battery? Yes, it is. So that is direct current. How about this computer?
Yes.
Yes. Most of your computers are direct current. Okay? But I've got it plugged into the wall, and that's alternating current, isn't it? Except for, look what it's going through. It's going through what they call, this is called an adapter, AC adapter. It adapts the alternating current coming in to the direct current coming out. Notice that's a much different looking wire than that one is. Okay? And that's because it's AC coming in, this converts it to DC, and that's what feeds the computer. So basically, if it's somehow associated with a battery, it's usually direct current, DC. And by the way, that's what I should put that, DC. Okay. Whereas on the other hand, current that changes its direction is alternating current. All right, here's Haley. Okay. Oh, this chair is so low it hurts. All right, Haley's here. All right, the middle part of the alphabet's here nicely, but the beginning and the end are not yet. Hopefully they'll get it. Well, Brianna, I know, is not going to be here tonight. She said that last time. So alternating current, we're in Chapter 17, Basic Electricity. We're in 17.5, Simple Circuits, and we're talking about two different types of circuits. Direct current, when the charges all flow in one direction, alternating current, which I was just about right, when they alternate their direction. We're just our start, 17.5. So alternating current is current that changes direction Okay, current that changes direction. All right, let's go back to direct current, that the charges flow in one direction. Do those charges move really fast? You would think so, because you touch a wire to a battery and the light comes on. But actually, the charges move incredibly slowly. Someone has figured it out. When you turn or hit your brake lights in your car, if you waited for that electron to go from where it makes the contact, when you press your brake and it makes a contact and closes a circuit that sends the electrons there, to the back of your car, which, what, 1 to 2 meters at most, okay, 6 feet at most, it would take several hours for that electron to get to the light. That wouldn't do any good. You'd already getting hit in the back by then. What it is, what was the last section talking about? Electric fields. The field is set up instantaneously, almost instantaneously. The charges take a long time to get there. Okay? Now, if I were to turn on the light switch back there, and if you need light, I can turn it on, the lights look like they come on immediately. They really don't. It's not that the charges that are sitting at that switch take off and go down the wires until they reach the light and do it almost immediately. No, the field is set up almost immediately, and all the charges start moving. Because guess what? The charges near that switch, because that's AC, alternating current, those charges do this. Back and forth, back and forth, back and forth, back and forth. They never leave from right near the switch. But see, every charge in the whole circuit does that. So the charges right at the light do that. As soon as the electric field is connected, when you hit the switch, then all those charges start moving at the same time. In fact, the ones right at the lights, and that's where you get the light looking like it coming on instantaneously. It's not quite, but it's awfully close. Okay? So, what do we mean by an electric circuit? And this chapter is called A Simple Circuits. An electric circuit I know the words are sort of similar, currents and circuits. They're not quite the same thing. What it is a conducting loop okay? A conducting loop in which the electrons remember, electrons are your charge carriers. The protons generally don't carry charge. They are charged, but they're fixed in the nucleus. They don't get to move. The electrons are free to move, so in which the electrons, which are your charge carrier, carrying the electrical energy, okay, may be transferred from a suitable source to do useful work and then return. from a suitable source to, I'm going to interject a word here, to do useful work whoops, that's only one L. Now, where that work is done, that's called the load, by the way, the load. You don't have to know that, but just giving you the idea. Okay, and return to the source. So the electrons start at a source, they go through the circuit, they do the work, and then they go back to the source. Well, wait a minute. Don't you use up the electrons when you're doing the work? No, you use the energy from the electrons to do the work. You're not using electrons, you're using their energy. So what is that source doing? That battery, that generator, whatever it is, it's giving energy to the electrons. Then the electrons, when they pass through the load, the place that does work, they lose their energy to perform the work, but the electrons all make their way back to the source. And then they're pumped up again, okay? Pumped up in energy. Now, an illustration of this, and this is just an illustration, let's say that represents a battery. Now notice one line is long and one line short. The typical convention is the long line is called the positive side and the short line is called the negative side. Okay? Now, we run into a little bit of a problem with electricity, and I almost blame it on Benjamin Franklin. He just sort of arbitrarily said, well, let's make the protons positive and the electrons negative. And when he did that, he got everything backwards. Okay? They can be named anything you want, but it just sort of messed up our things. So let's say from the battery, the electrons go through a wire, and then they hit, and I'm going to draw it as this. That's going to represent our light bulb, or whatever else is using the electricity. And then it goes back. Now in the book, they show a switch. I'm going to leave the switch off. The switch either opens or closes the circuit. Okay? Now this is illustrating what we have. This is your power supply. This is your energy source. That's the battery. The energy source. If this was a flashlight that you're doing, you close the switch, the light comes on, the energy source are your batteries. That's giving the energy to the electrons. The electrons start making their way around, but it really doesn't matter that they make their way around. The electric field is set up as soon as you close that switch, and all the electrons in the circuit start moving. Now here's where the problem comes. Here is what we call our conventional current. I'm going to give it the symbol I. And this is the conventional current. That would be the direction positive charges would move if you had positive charges. Of course, the electrons are negative charges. So in reality, and this is called the conventional current, and you don't need to know this, but I'm just giving it to you. Conventional current, that's what you would expect if you had positive charges. Really, you're having electron current, and that's going in this direction. Because you have an excess of electrons here, they move around to where you have a deficit of electron. So this is your electron current. Now don't sweat this. Don't worry. It really doesn't matter that much. Okay? Basically, what really matters is your field. I'm sorry, hopefully that'll come back on. Yeah. I just had to adjust my thing. Okay? Now, I've just labeled the necessary components of an electric circuit. You need a source, okay? You need a pathway, and you need a load. something to use the energy the source gave, the source to provide the energy, and then a pathway, a circuit, complete circuit, to transmit those electrons. Okay? So there's your basic configuration of that. So let's talk about the source first, and that's what supplies the electrical energy to the charges. So I think, is it all right? I'm going to erase this slide because I need to do more writing. Okay? So let's start with the source. That's the battery, basically. Okay, the source is the object that supplies energy to the charges. And by the way, I used the term earlier but didn't actually define it very well. Your current is the rate of using charge. So it's the amount of charge per unit time. Is the rate of moving charges. So your charges are coulombs. Your rate of coulombs, the change of coulombs per change of time, that's your current. And later we'll give that the name amperes. Okay, we'll get there later. So this is the source of the object that supplies the electrical energy to the flow of your charges, which are usually electrons. Now, they talk in the book about a dry cell. They've used that term a couple of times. That's just one source. In a flashlight, that would be a dry cell. It can be a battery, a cell generator, an outlet where you plugged into the wall, or any other device that either produces or stores electric energy. Okay? A student who was in my classroom when I went to get my computer out, she was there for a biology class that was going to start in a short period of time. She started talking about how she uses a, goodness, what did she call it? It basically was a electric storage unit, okay? My wife has one too. She charges it up, and then when she wants to charge her cell phone or her iPad or something like that, but she's not someplace she can plug it in, she can just plug it into this storage unit, okay? So anything that would hold that charge, okay? Now, you have to have conductors going from the source and to the source, okay? And those electrons go to, say, your first load. Say if that happens to be my computer here, maybe the second load is the projector, okay? If all these were in the same circuit, they're not, but you could just imagine that being the case. You may have multiple loads, and each load uses the energy the source provided to the charges, okay? Now, all right, to erase this?
Yes, sir.
Okay. I'm going to go to the first slide that we find useful here, and this is making what they call the water pump analogy between electricity and something we're more interested in or used to, a water tower, okay? What your battery does for you, your electrical energy source, there's chemicals in the battery. In your car, it's sulfuric acid and a combination of lead plates and lead sulfate plates, okay? And anyway, the electrical energy goes from the place of low energy to high energy. Quite often, okay, they have the electron flow here, not the conventional flow. This is electron flow. What the battery does is pump up the charges that the electrons receive. So they have high energy electrons here, low energy electrons here. You pump up the energy, so these electrons have more energy. Okay? Then the electrons flow this way. Here's your light bulb. The light bulb uses that energy to provide you light. And if you've ever touched a light bulb after it's been on for a while, you know it provides heat too. Okay? So that's the use of the energy those electrons have. Then the electrons continue flowing back to the low energy side because you've used up the energy here. So now they're low energy electrons. The battery pumps them up again. Okay? And it'll keep doing that as long as the battery has adequate charge. Okay. Now, what is that equivalent to? That would be over here. Any of you live near a water tower? You've seen water towers, right? Somewhere at the base of that water tower, there's pumps. And what you're doing is pumping water up into the tower. Okay? Now, you're not creating water. The water is there. But you're pumping the water up into the tower. What are you doing? The pump is giving energy to the water. Gravitational potential energy. Remember when we did this in chapter, what was it? 12 maybe? Or yeah, okay. When you gave energy to the water by pumping it up here. The water's there. Then it comes down here and you could use that to turn a turbine to produce electricity, okay, or anything else, and then you pump the water back up again. So you see the water is like your charges here, the electrons. You're not using up the water, you're using the energy from the water that you got when you pumped it up to the tower. So the pump is like your battery or your energy source, okay? It's giving the energy to the water or to the charges. Your turbine is like your light bulb. This is what's using that energy to turn this and maybe make the merry-go-round go around or something like that. That is what's using that. That is your load, what I've been calling the load. So you don't use the water, you use the energy of the water to turn the turbine. Of course, the water is flowing by. Now, here's one place where this analogy breaks down. If you had dug into the ground or something like this and you hit the pipe and broke the pipe, the water would come flowing out. Okay? Not good. Over here, if you hit the wire and break the wire, the current stops. It doesn't go flowing out and spilling on the ground. It stops. Okay? So that's the difference. The current and the water, they change a little bit there. Okay. So that's your illustration that's at the bottom of page 461. They call it the water pump analogy. Okay? So that's talking about the source, the battery equivalent to the pump. Okay? Now we'll come back and talk more to get to this slide, but for right now, let's go back to our other slide. All right. And continue. So that was dealing with the source. Now we're going to deal with the conductor. I called it the pathway, the thing that conducts the electricity from one place to another. So this is the conductor. Whoops, got to get my pen back. Okay, what is a conductor? Is a material, okay, that transfers the charge to the load. But it also transfers it back again, back to the source. Because your load is not using the charge, it's using the energy of the charge. Okay? So your conductor also transmits those charges back to the battery. Okay? Now, what are your common conductors? The most common conductor of this material is copper. Copper has several advantages of being a good conductor. Okay? One is it's a great conductor. It doesn't lose a lot of energy. It's not the best conductor. Actually, the best conductor is silver. But why don't we use silver wires? Way too expensive. Okay, but not only that. Copper wires bend easily. Okay, silver is more brittle. So you wouldn't be able to bend the silver wire. It would probably tend to break on you. If you were to use that, it wouldn't be a good idea. But after silver, copper is the very next, and they're really close to. So we usually use copper. Not always, but silver's better. Aluminum's not quite as good, but aluminum's a pretty good conductor too. Okay? Now, there are other materials called insulators. So a conductor moves the charges very easily. Now they give the illustration here, and I really don't care for it too much, but I'll give it to you. As long as there's not much restricting the flow of these charges, these are all negative charges here, and not much is restricting, that would be called a good conductor. However, other materials might have lots of opposition to it, okay? And this may take off and go in this direction, that direction, this direction, this, and they don't go very smoothly. Those would be insulators, okay? They are poor conductors, okay? Now, they are substances that do not allow electrons to pass readily. Substances that do not allow electrons to pass easily, readily. I think they use readily in the book. Okay? Readily. Now, what are some good insulators? Anyone know?
The stuff that they put in our house, you know, the cotton.
Yeah, okay. Yeah, when you're having dental work done? Yeah, because you don't want good circuitry in your mouth. In fact, let's go back to the battery idea. Remember, that was a chemical reaction that gave energy to the charges. Now, I've asked this question before when I've taught automotive mechanics, which are mostly the young guys. And when I ask the question, they say, oh, yeah, sure. And that's not really what I meant. I said, have you ever had a battery in your mouth? Most people say, no, we don't put batteries in our mouths. Do any of you have fillings in your teeth? I do. You don't? Okay. Okay. You've never experienced this then probably. If you have a filling in the tooth and you happen to bite down on a piece of aluminum foil, you know it. Because what happens is you have that chemical reaction in your mouth. You have two similar metals. You have silver that's in the filling. You have aluminum, okay? And you have a very good conductor, your saliva. And suddenly, if you do that, suddenly it sends a charge through that conducting material, your saliva. And guess what is real close to where that filling is? Your nerve, okay? If you have a complete, tooth there, they haven't had a, what do they call it? When they drill out your tooth and you deaden the tooth. If you've got a nerve there and you bite down on that piece of aluminum by mistake, you know it, okay? Immediately you know it. You've just felt a battery in your mouth. Not a very strong battery, but a battery. Okay. Now, so most metals are good conductors, and most other things are usually pretty poor conductors, making them insulators. Now, have you ever watched the linemen when they are working on the wires outside? Generally, they're always wearing big, thick rubber gloves, because rubber typically is a terrible conductor, a very good insulator. They say if you're, and I bet the other thing they wear, whether you realize it or not, very thick rubber-soled shoes, because again, it's a good insulator, a very lousy conductor. All right, now there's another type of materials. I've got to sneeze there. Oh my, sorry. There's another type of material, and very few of these, small number of materials, called a semiconductor. Okay, small number of materials are semiconductors. Okay, now what makes a semiconductor? They fall in between conductors and insulator in their ability to conduct electrical energy. The importance is due to the fact that these materials, under certain conditions, allow current to flow in one direction only, and in other conditions, they do not allow current to flow at all. So semiconductors are neither good conductors nor good insulators in their pure form. However, they become excellent conductors or insulators when an impurity is added, and this is what makes a transistor. Now, you don't need to know all that, and it's just a bit long to write down, but silicon is a pretty good semiconductor. It conducts electricity in one direction only, and that's why they call Silicon Valley, because they made semiconductors there. They're used in computers, electronics, all sorts of things. Selenium is a semiconductor used in the process of making photocopies. So every time you use a Xerox machine or any machine like that, and even really printing, you're using selenium, which is a semiconductor, and when the conditions are right, it sends the current through very easily, and when they're not right, it blocks it. Okay? So those are semiconductors. Now there's another kind, and this is very rare too, and that's a superconductor. Okay? Again, a very small number, but these are materials, not very many, that continuously conduct electricity without any loss of energy. Now, a copper wire, a silver wire, they're great conductors, but they always lose a little bit. A superconductor does not, ever. Now, two features of superconductors. They have to be incredibly cold. Normal thing that would be a superconductor at normal temperatures is not going to conduct well at all. But if you get the temperature low enough, suddenly it becomes a superconductor and doesn't have any resistance to the flow of the charges. They're very rare, and a guy named Heikki Kamerlingh Onnes discovered superconductivity in 1911, shortly after he discovered how to liquefy helium gas. Okay, and so that he determined that mercury metal lost its resistance to the flow of electricity at temperatures just below 4.2 K. That is incredibly cold. That's like minus, let me see if I can remember, 200 and some odd degrees Celsius, which would be minus 465 degrees Fahrenheit. That is cold. It is incredibly cold. Okay. So, we have our conductors. We had our source. We have our conductors and insulators, semiconductors and superconductors. Let's move next to what I've been calling, and finally the book is going to call it, the load. Can I erase this? Okay. The load. I have to raise this up again. Okay. What is the load? In the load, the load in the circuit converts the energy, electric energy, from the source, which is your battery or your circuit or whatever, from the source to useful forms of energy. Okay? For instance, the light. That is your useful form of energy. The load, that projector is the load. It takes the energy that came from the power plant, wherever that was, where you had your generators making the electricity. It takes the energy from that, converts it into light. Now, if I were to hold my hand in front of that lens up there, I'd probably feel a fair amount of heat as well. And there's a fan on one side or the other there, I could feel some heat. There's always some energy that's lost to heat, but most of it, we hope, is going into the light. Okay? So other forms of energy or work. For instance, that pump that pumped up the water in the tower, that would be converting the energy from electrical energy to useful energy, increasing potential energy. So the next topic is current, and we've already sort of talked about that a little bit. Let's give a sort of a better definition here. The flow of electrons, I can't spell or write or something, okay. I get the writing too fast. That is what we mean is a current. The flow of electrons through a conductor is the current. And again, it's measured in charge. I wrote Q because that's what we use. Charge per unit time. Okay? That's what we mean by current. Okay? The flow of electrons through a conductor is the current. Here are the units for it. 1 amp, that's current, is equal to 1 coulomb, that's charge, in 1 second. That's your time. So an amp is a coulomb per second. Now, by the way, amp is capitalized because it was named after Louis Ampere, a French physicist, lived about the same time Coulomb did, about the same time Benjamin Franklin did. So I'm sure those guys got together sometime when Franklin was the ambassador to France. Okay? Coulomb measures charge, named after Charles Coulomb. Okay? Second is just a unit. It does not named after anyone, so that's a lowercase letter. C is capitalized, the A is capitalized. All right. Now, This isn't quite the right slide, but I'm going to use it anyway because I don't want to have to draw it. Let's go to this one. I'm going to use it later for something else. But we've seen something very similar to this already. Goodness gracious, I'm stiff and sore. Okay. Here is your battery. Looks like maybe a 9-volt battery there. That's your energy source. That battery has chemicals in it that pump up the energy going to the electrons. Okay? Now they have it going through a switch here. The switch is open, so nothing's happening. Nothing is happening. You're not using the energy here. Nothing's happening. The light's off. Okay? But as soon as you close the switch, now you have a complete circuit. The electrons now can flow between the source and the load. So there again, this is our pathway or the circuit. Okay? Here is that same symbol diagram. Okay? Here is the battery, the plus side here, the minus side there. The top long line is plus, the little sign is minus. Here is your load, the light here. Here's the switch that either open, nothing's happening. As soon as you close it, then you get current flow through the pathway. Okay? Now, before they showed the electron current, which flowed that way. This is conventional current flowing that way. It really doesn't matter which way you have the current flowing. It just has to flow. And the current is the carrying charge. It's the movement of charge, which is Coulomb per unit time. That's an ampere. And that's when the charges are moving. Even if they're just moving back and forth, back and forth, back and forth, like alternating current, they're carrying the energy that your source gave. Okay. So, again, I'm going to mention this. This would be, I'm going to get my pen back. Okay. This shown here is what we call the conventional current. That goes from plus to minus, and this would be, they sometimes call it, our book calls it, the positive current. In reality, most of the time your charge carriers are electrons, which are negative, so they go from negative side. This would be your electron current. Which, let me get my thing back up here, is called the negative current. Okay, because it's the negative charges moving actually where they go. All right, let's go back to, our other slide. Now I've got to get my pen back again. Okay. And let's talk about another concept, and this is voltage. You heard of voltage? Yeah. That's how you usually rate your batteries. I said it before, that looked like a 9-volt battery. Your dry cell batteries are usually 1.5 volts. You know, your car battery is usually a 12 volt. Okay, you rate your batteries by the voltage. Okay, now what do we mean by voltage? Okay, the reason the current flows is you have that power source, right? That energy source, the battery, which is pumping up the energy of those charges and moving them through the wire. Okay? That's why they move. Okay? Now, those two poles of the battery, one's called positive and one's called negative. Okay? Because they're at different energy levels. Okay? The voltage is a measure of that. The voltage is usually associated with the battery, and what that is, it's a potential difference. Remember, we talked about that when we were talking about you're raising the book off the floor, giving it more gravitational potential energy. This is electrical potential difference. And what that is the work or energy, work and energy, same thing, per unit charge. Those coulombs again, okay? It's the work or energy per unit charge. That's called your potential difference. Now, in the old days, they called that the EMF. And in the old days, that stood for, and by the way, the symbol for that is E. Now, that's not the same as your electric field. That symbol was also E, but in circuits, E stands for the EMF. In the old days, that meant electromotive force. But it really wasn't a force, so they quit calling it electromotive force. They just call it EMF, because that's what they used to call it, but they don't call it electromotive force. But the symbol for it is usually E, okay? Now, you'll see they use a couple of different symbols for voltage, okay? Now, in a circuit, remember your battery pumps up your voltage. It gives more energy to the system. Energy per unit charge, that would be the voltage of your battery. Now, quite often there, that's what they call the E part, okay? In your load, okay, this is in the circuit source, you pump up the energy, okay? In the load, you use the energy, so the energy goes down, okay? So that would be a voltage sink. And there they usually refer to that not as E, but as V. They're talking about the same voltage, but it's just whether it's being built up, E, or reduced, and that would be the voltage drop, we call it. And quite often they'll use the symbol delta V, meaning a change of voltage. You drop the voltage as it passes across the load. Now, there was an interesting little history here. The guy who first, or given credit for first discovering the first battery, was not a physicist by trade. He was an anatomist. He studied body parts, okay? And he was busily studying the biology of a frog. They had killed a frog, put the frog into formaldehyde to keep it from rotting, okay, and spoiling. Still stunk like crazy because formaldehyde stinks, right? And he had cut off one of the legs, and he was studying, looking for the muscle tissue, the nerve tissue, the other tissue in that excised or cut off frog leg. Now, the frog had been dead for weeks, probably. The leg had been cut off for a long time. And what he had a pair of tweezers. Now, I don't know what the tweezers were made of. I'm just going to make something up and say they were made out of steel, okay? But he had a little probe, a little needle thing. Now, let's just say it was made out of copper. I don't know if it was, but let's just say it was. And while he was studying the frog leg, holding it with his tweezers, and it still had lots of formaldehyde in it, which formaldehyde actually turned out being a very good conductor. And he had this little probe, and he was trying to separate the muscle tissue from the nerve tissue and stuff. And when he touched the nerve tissue, the frog leg twitched. Okay, this frog leg from a dead frog who had been died for weeks, and it had been cut off the rest of the body of the frog, and yet here it twitched on him. And he probably almost had to clean his pants. I mean, he was just so shocked by the fact that he had just seen the frog leg move by itself. Okay, he didn't move the frog leg, it did it by itself. What he had just done, without realizing it, he had made, in a sense, the first battery. Because he had two dissimilar metals, one steel and one aluminum or copper or something like that, and a good conductor in between, the formaldehyde. And when he did that, then the muscles twitched, just like they do, because your body is an electrical machine. Your nerve cells are a very fine potential difference between a sodium ion and a potassium ion. This is really oversimplified, and that's what sends the signal through your eye. That's why you can hear me talking now. That's why you can see and read what's on the board. You have electrical signals going constantly through your system, your eyes, your ears, and everything else, and going to the brain, and your brain is translating it and doing it almost instantaneously, just like the electric fields, okay? So here you have the voltage drop. And okay, so that was a guy named Luigi, maybe, Galvani. He was an anatomist. And they actually named the unit a galvanometer, the thing that measures voltage. Well, he was Italian, and he had this friend who was also, I assume they were friends, also Italian, and when he told him about it, he was no longer interested. Once he thought he had no longer discovered the source of life, but had just happened to make the first battery, he had reported this, and this co-worker named Alessandro Volta was actually a physicist, and he was really interested in this concept of voltages. Well, they didn't call it that, the EMF, potential differences, and guess what? They named the unit volt after him. Now, I was very lucky. My wife had professional meetings one summer over in Italy, a beautiful area of Italy, northern Italy, called Lake Como, right below the Swiss border. I mean, just right near the Swiss border. It's actually three beautiful lakes there. Lake Como, the town of Como is on Lake Como. And Karen had taken her niece over with us too. And while Karen was in her meetings, having them report her papers and go and do all the scientific stuff, we were out wandering around this beautiful city of Lake Como. And we saw this almost looked like a temple, just a little shrine over here. We said, well, let's go see what that is. We went up to it, and it was a shrine dedicated to Alessandro Volta, because that was his hometown. And that's where huh?
Where was that?
Lake Como, Italy.
Oh.
Yeah. And we went through that and saw some of his very earliest batteries that he had made. They had them on display there. You couldn't touch them, but you could see them. And they actually called them piles, P-I-L-E-S, okay, which reminds me of hemorrhoids, but I don't want to get into that, okay. But anyway, the volt was named after Alessandro Volta. And here is the definition of a volt. 1 volt, and the symbol for volt is capital V, named after Volta, okay, is equal to, and what do we say it was? It was energy per charge. That's 1 joule of energy, that's joule, per unit charge. 1 coulomb of charge, named after Charles Coulomb, and that is capital C. So a volt is a joule per coulomb. All three of those named after people. Okay, so all three of them are capitalized. Now, moving on from there. Oh my goodness. Goodness, I talk too much, don't I? Let's move to the next concept. There was voltage. Now let's talk about resistance. Okay. Oh, and by the way, Hallie, we were talking about this before, and before we go tonight, I probably need to go over the end game for the term, so remind me to do that. But we were talking about Sharon said she may or may not come Thursday night. Did you have any objections to either pepperoni or cheese pizza? Are they both okay for you?
Fine.
Either one?
Yeah.
Pepperoni's fine. Okay. We'll find out on Tuesday if Sharon's going to be here or not. If she's not, we'll probably just get one pepperoni pizza. But if she is going to be here, we'll get a pepperoni and a cheese. Because I like them both. And I know Brianna said she couldn't do cheese, but she liked pepperoni. And I don't remember if Krishana said anything or not.
She didn't have a preference.
She what?
She didn't care.
She didn't say?
She didn't have a
preference. Okay, but she could do them both. So we'll talk about that on Tuesday. Okay?
I won't be here Tuesday. I'll be out.
Oh, you'll be out Tuesday, but you will be coming back to turn in your test. That's when we're talking about having the pizza is on Thursday, not on Tuesday. We'll talk about it on Tuesday, but we'll have it on Thursday. But Sharon said she might come turn in her test on Wednesday to keep from having to make a special trip here Thursday. So if she does that, we may only get one pizza of pepperoni. Okay, that's why they came up. So let's talk about resistance. Not all substances or not all, even all metals are good conductors. Those with few free electrons tend to have greater opposition to the flow of charge. So resistance is the opposition to an easy flow of charge, to current flow. And remember, current flow is charges per unit time to current flow. That's what we mean by resistance. Now, there are several factors that determines resistance. Okay? The first of these is temperature. Okay? When you increase temperature, you increase the resistance in a wire. Okay? We'll get back to this in just a moment. The second of these is the length of the wire. Okay? And that kind of makes sense, doesn't it? I don't know if you've ever had connected one hose to another hose to another hose to another hose, trying to carry the water for a long distance through hoses. When you do a bunch of those, the water trickles. It doesn't have as much energy because the more the length, the more resistance you have, and the less energy the water has. So length is another one. The longer the length, the greater the resistance. A third one, and I hope this one sort of makes sense, is cross-sectional area. Okay? Now, what that means, I think I've used this example before. Have you ever sipped coffee, hot coffee, through that tiny little straw that they use as a stirrer? Okay, and you can suck the coffee through that because coffee is really thin. But if you took that tiny little straw and tried to suck a milkshake through it, you'd probably pop your eardrums off, right? Because the smaller the cross-sectional area, the more resistance you have. Because the coffee's hot, it flows through anyway. But if you add any more resistance, it's not going to flow through. So cross-sectional area, the smaller the area, the greater the resistance. Okay? And then the fourth is the actual material. And we've talked about that before too. Okay? Copper would be the best, next to the best conductor. Silver's the best, then copper. Aluminum's pretty good. Gold is okay, but then anything past that. Iron is not particularly great, and you get on down, and other forms are even worse and worse and worse. So they become almost insulators. Okay. Now let's think about, okay, y'all are familiar with the old incandescent light bulbs, right? The ones, okay, not the fluorescents, not the LEDs, the old kind of light bulbs. Have you ever seen one of the clear ones and noticed what's inside? Yeah, okay, she just did this. A tiny little filament. That filament is barely the thickness of a human hair. And it's coiled up in a coil. Okay? and it's made out of a different material, typically titanium or something like that, which does not conduct electricity well, okay? It has more resistance. So let's think about that. That filament, because it's wound up in a coil, if you were to stretch that thing out, it would be really long, right? And its cross-sectional area is incredibly tiny. So both of those make for more resistance. And the fact that it's a material called titanium or something like that is not as nearly as good a conductor. Well, why did Edison use that material? Because when it gets hot, which is what happens when it has a lot of resistance, it begins to glow a whitish color. And that's why he used it, okay? Because it would get so hot, because of so much resistance, it would start glowing. And that's how the old light bulbs work. Now, I want you to think back to when you've ever had a light bulb go out on you. When was that? Name what you were doing that the light bulb popped out.
In the kitchen.
And okay, and what did you do?
Took it out.
You what?
I took it out.
Okay, yeah, but before, when it blew out, what were you doing when it blew out?
Turn on the light switch. Turn on.
Oh, it's when you turned it on. Well, why would it blow out when you turned it on? Here's why. When you first turn it on, the temperature is cold. And the colder the temperature, the more current flows, okay? When the light bulb's been on a long time, it typically doesn't blow out on you unless it's just been on forever and finally goes, okay? But it's usually right when you turn it on when it's the coldest temperature. Why? Because your resistance is the least when it's cold, and therefore more current flows and it blows the bulb. When it's hot, more resistance. And so you see in the light bulb, you can see all three of them. The material is tungsten, cross-sectional area is incredibly tiny, the length is fairly long, and the temperature, that's when you usually blow the bulb when it's cold. Okay? So you see all of those features right there. And I'm afraid we may have just run out of time, have we? So we'll start next time with the formula for that. And here we'll do example 1, so we'll wait and do the homework exercises when we do that. But let me, before you go, do two things. First thing is give you the last test, okay? Oh, did I give it to you?
Well, no, it's the 16.
Okay, is that the one on frequency?
Oh, we gave the test. Oh, okay.
Yeah, this is the test, the last test that we'll have. And remember, Brianna needed one last week, and I just happened to have one. And here's one for the two of you.
And then
Oh,
this is.
there's that one. Okay. And there's that one. Good. All right. I'll try to have these graded next time.
Which ones did you were saying?
Okay.
You weren't familiar with? Which ones did you want us to do?
Okay, yeah, that's what I was going to say. We haven't finished the chapter yet, so you may not be able to do this. But you should be able to do number 1 now, because that's Coulomb's law. Number 2 is Coulomb's law. We've done that. Number 3 is Coulomb's law. You should be able to do that. Now, you probably can't do number 4 yet. The formula we were just going to get to just now will be that one. So you can start on the first 3, and then number 6 we'll do next time. Number 7 we'll do next time. Number 8 I think we'll do next time. Number 9 next time. And number 10. So you can only start on the first 3. I mean, you can try doing any of them you want to, but we've already covered materials for 1, 2, and 3. But I want to give them to you so you could at least get started so you wouldn't have as much pressure at the end. All right, now, the other thing I wanted to go over really quickly, what my schedule was next time because you weren't here to hear it. Okay? Next Monday is a regular class day, so I have office hours on the Bessemer campus from 8 to 8:30 Then I'm in class from 8:30 to 5:30, and I'm back in the office from 5:30 to 6. Bessemer campus. Okay. Tuesday, regular class day. I'm on the Bessemer campus, 8 to 8:30. Have class 8:30 to 10:45. But then here's the bad news. I'm only in the office from 10:45 until 1:45 because I've got an eye appointment at 2 o'clock, but it's right across the street from the Bessemer campus at UAB West. But it's probably going to take between 1 and 2 hours. Last time it did, so I was really disappointed. I thought I'd just get over there, get it done, and go back. Didn't happen that way. Okay, so I'll be out of the office from about 1:45 till probably close to 4. Okay, but then at 4:15, I'll be coming over here to this campus, and we'll have our last class on Tuesday. I hope to get here before 5. And okay, now Wednesday is the first day of finals. That's the finals for the Monday, Wednesday classes. So I'll be in the office from 8 o'clock in the morning until, unfortunately, 12:30. Because they've called a meeting on the Birmingham West campus at 1 o'clock. So I have to leave Bessemer to come over here. I'll be over here from 1 till, I'm guessing the meeting will probably go about 2 hours. It's one of those that takes a long time. So that means I'll probably be out of the pocket from 1 to 3 or something like that. Then when I get out of the meeting, I'll go back to my office over there, which is in B122. So I'll be there. And that's why Sharon said she might come bring her tests then. Okay, that's why she said that. So we'll find out Tuesday whether she's going to do that or not. So anyway, I'll be in the meeting, but then once the meeting's over with, probably 3 to 6, I'll be in the office over there. Okay, then on Thursday, that's the Tuesday-Thursday final day, I'll be in the office from 8 in the morning until about 4 o'clock in the afternoon, and that's when I'll leave, pick up the pizza, come over here, and we'll meet from, I'll be here from 5:30 till 5 to 6:30 as normal, so anyone who wants to come anytime during that time, you can have pizza. I'll try to grade your test if you turn it in then, and I'll let you know what your final score was and everything like that.
Okay. Can I ask a question?
Yeah.
If we can turn our test in on Tuesday,
right.
Can you grade them and give us our score?
Probably.
Okay.
But you see, it'll have to be after class is
Right.
over. Yeah,
I
okay.
can wait.
Yeah, I can do it then too. But you see, we haven't even covered all the material for it yet, so we'll be covering that material Tuesday. So it'll be a little tough, but if you can do it, yeah, I'll do that. I'll be glad to do that. But then, so if you want to try to even leave earlier, you can do that. So read the chapter. All the lectures are out there on the YouTube,
Okay.
and you can watch those. And if you can get all that done, fine, fantastic. And then you won't have to come Wednesday or Thursday. All right.
All right. Thank you. Have a good week.
All right, you do too.
Good night.
All right.
Well, we did, yeah.
What's that?
We did.
Yeah.